Good morning. My name is Neil Rowson. I am Laboratory Manager at Buntings in Redditch and also Emeritus Professor of Minerals Engineering at the University of Birmingham. Today we're presenting another one in our series of technical overviews of separation equipment manufactured at Buntings in Redditch. Today we're going to talk about the electrostatic separator and its potential applications in the recycling industry and also the minerals industry. The talk should last about 15 to 20 minutes. I hope it's going to be of interest. So first of all, electrostatic separation relies on the charging and conductivity of particles to achieve a separation. There are three main methods of particle charging. First of all, by ion bombardment, or corona charging as it's called, which is the principle used in the Buntings electrostatic separator. There's also charging by induction, and there's also triboelectric charging or frictional charging of the particles usually by agitation of them, so the particles rub together and a frictional charge is occurred on the surface of the particle. This technique tends to be used more on very fine particles in plate type separators. So just to confirm that the unit manufactured by Buntings in Redditch tends to use the charging by ion bombardment or corona charging technique to obtain a separation. Corona charging is induced onto particles in the separator by the use of an electrode, as we see here. That electrode is either positively or negatively charged. In this case, we tend to use positive ions to charge a particle as it comes into the separation area. So we have positive ions charging our particle, which could be a conductor or a non-conductor, and that particle is carried into the separating area on an earthed roll type unit in this case. So the surface of the roll itself is earthed, which allows a separation to be achieved. So if we see for a conductive particle, which are the C particles here, as it's charged, and the material passes through the separation zone, we get a positive charge forming here, a negative charge forming on the base of the particle. However, because it is a highly conductive material, that charge as it builds up is instantly dissipated through the earth roll and goes to earth, which means effectively a conductive particle remains unaffected by the corona charging system and will just fall off the roll by its own centrifugal force. However, a non-conductor or insulating particle, like a plastic material, for example, N here, is charged in a similar method to the conducting particle, but because it will not release its charge to the induced roll, we get a difference in charging here, which creates an adhesion of the particle to the roll surface, which means it sticks to the roll surface for a short period of time. That charge will eventually dissipate, but much, much slower than the conductive particle. So consequently, it remains attached to the roll surface and a separation is able to be achieved. So our conductive particle really loses its charge within a few milliseconds and is thrown by the centrifugal force Fc. Our non-conducting particle has a charge remaining and an image force, and that image force is Fi, and that sticks it to the surface. If you want a good analogy for that, just consider the old game that used to be played at children's parties, where you take an inflated balloon, rub it on your jumper, create that static electric charge on the surface of the balloon. The balloon's an insulator because it's rubber. You can then stick it on the wall, and that charge will remain for a few seconds and allow the balloon to stick on the wall until the charge slowly dissipates, maybe over 10-20 seconds, and the balloon will eventually fall off the wall due to gravity. It's exactly the same principle. So consequently, if you look here, what happens is we have the concept of image force, which is Fi in the last slide. So we have our grounded roll surface here, and we have our non-conductive particle, which may be plastic, glass, or a non-conductive mineral like silica, sand. We get our surface charge of negativity there, and we get what's called an imaginary or image force here on this charge, and that affects that positive, negative charge, basically sticks that particle to the surface for as long as it takes for this charge here to dissipate. And because it's a very slow release of charge across this barrier here to the Earth's surface, because it's a non-conductive particle, that will remain long enough for us to achieve a separation, providing we've got a correctly earthed roll made of the correct material. So we have the concept of image force. So if this is our electrostatic roll here, and it's revolving round like that here, we have our particle here on the surface. We have our electrode situated here, which is producing our positive corona charging. There will be a number of forces on that particle. There'll be gravity, Fg. There'll be air resistance as it passes across the roll, having been fed on by the vibro feeder. The roll's revolving. And the key ones that we use for separation are the centrifugal force generated by the roll speed, and Fi, which acts in this direction, which is the image force. And that image force is defined by the charge we put on this electrode here, and also the conductivity of the particular mineral that we're processing. So if it has a low conductivity, the image force will be high, which means it sticks on the surface all the way around here and will be removed by a brush at this point here. If it's a conductor like aluminium or copper, it will instantly lose its charge and be thrown off by the centrifugal force generated by it passing over the roll, which is a function of its mass, its velocity squared, and the radius of the roll that we're using. So it's a balance of those forces that allows us to separate between a conductor and a non-conducting particle. So if we look at a electrostatic separation in sort of in animation, we have our corona electrode here, which will be running at 20 to 30 keV. So it's high voltage, very, very low current. We feed our material on by a vibratory feeder. The material falls on the roll. I can control the roll speed. The roll is earthed through the bearings. The yellow particles are conductors, which may be aluminium or copper. We have a middlings fraction here, which may be particles that contain both copper and plastic on them. And here we'd have our insulators, which will be something like, it may be a granulated cable, a very fine granulated cable. So this may be the plastic sheathing on the PVC sheathing on the cable itself. PVC shielding is insulator. It sticks on the roll because of the image force, and is discharged at this point by a brush system here, which has the effect of aiding discharge, but also cleaning the roll surface before it rolls back in to pick up some more feed material here. So really the separating zone of the separator ranges from about here to about here in nature. The material is charged as it drops off the roll here, off the vibratory feeder here, and it's the sphere of influence where the material is charged is in this area here. I can control the separation efficiency by controlling the roll speed, the splitter plate position, which can be cut in here or cut in here depending on my wishes, and the kV that's applied to the electrode here. Typical kVs run between 20 and 30 kV. If you go too high, and it's always tempting to think that more charge will improve the separation, what you'll get is a random discharge to the roll surface of the electrode, almost like a lightning strike in a thunderstorm. The effect of that is that it breaks down the electric field for a nanosecond or two, which means that there's no no field operating, which means that your separation efficiency drops off quite quickly. So it's always best to run the separator with no spark discharge. So here we see the feed. Always feed via a vibratory feeder to get an even monolayer of material. Obviously, it gives you a more effective separation. We tend to use a stainless steel roll, earth stainless steel roll, because that has the correct conductivity for these sorts of applications. The other option would be a titanium roll, to all intents and purposes. So the principle of operation, if we just run through this again, before we look at some actual applications, we feed a material like a granulated copper cable. We feed it in a controlled monolayer onto our revolving earth roll. Voltage is applied to the corona discharge electrode, which is typically tungsten wire, which generates our electrostatic field as the particle drops off the vibratory feeder. Conducting particles like copper or aluminium instantly lose their charge because they're highly conductive and are thrown off the roll by the imparted centrifugal force. Insulating particles like plastics will keep their charge due to the image force that we discussed earlier, and it pinned to the roll for long enough for it to just revolve around the roll into the non-conductor's separating area and to be discharged, usually by the brush. Usually that image force is quite strong on an insulating particle. So we achieve that separation by the balance of forces between the centrifugal force and the image force itself. So this is an example of a electrostatic separator manufactured by Bunting's Redditch. So here we have the stainless steel roll itself, and what else? We have the vibratory feed. It would feed in at this point here onto the surface of the roll at this point here. What you can see here is the green areas here. There is an electrode that passes across there, which is a tungsten wire electrode. As material is fed on to the roll surface by the vibratory feeder, our non-conductors will stick on the roll and discharge into the non-conducting separating area. Our conductors will be thrown and separate off here. We may have a middling fraction which will come off here. I can control the separation by adjusting the splitter plates, which are here and here, and allow me to cut into the feed as I visually observe the separation taking place. So my control variables are my roll speed, which is controlled via the panel here. The voltage I apply to my tungsten electrode, which is controlled on this panel here as well, and also my splitter plate position, which is controlled by these two adjustable handles at this point here. We don't normally the electrode position is a reasonably constant in the separation process, because it's never good to vary too many variables in an experiment at the same time. We normally set the electrode position to be at about 45 degrees to the feed, as it were, and however we can adjust that depending on if we need to change the separation at all. But typically we run at 45-degree angle, and we're normally probably in the region of 50 millimeters from the surface of the roll. But again, that can be moved in and moved out accordingly depending on the particular application. So we have a lot of variables that we can control in the separation itself. Other things in the actual separation unit, there's a light in there so you can see what's going on. And also we manufacture them with heaters to control the relative humidity in the separating area as well. There's also dust extraction vents available in the design as well. So the different models that Bunting Redditch make, there are 3 different sizes designed to handle different capacities depending on your application. 0.5 meter, 1 meter, and 1.5 meters in roll diameter. roll width, the roll diameter remains a constant for all separations, and at 1 meter diameter unit will do about 2 tons per hour of a typical sort of ASR, auto shredder residue product. We'll come to some capacities a bit later in the talk. So we've got a number of variables. We've got a lot of variables for electrostatic separation. There are material variables, first of all, which is the particle size range of the material. The separator works in a size range really of plus 45 microns minus 4 millimeters, so it's a reasonably wide size range. The key thing about it is for scrap recycling applications that it does effectively process and is at its best performance below 2 millimeters in size. So whilst an eddy current performance will often drop off once particles get below 2 millimeters, the electrostatic separation is in its main separating zone. So it acts as another way of separating very fine granulated cable or auto shredder residue, and as a way of recovering valuable materials from a product that previously has been quite difficult to have an efficient separation on. Low moisture content in the feed, because surface moisture on the particles that are fed into the material can mask the actual material's intrinsic conductivity, then it's important to have low surface moisture and a free-flowing material. That doesn't mean to say it has to be thermally dried. It just means to say that it has to be it can't be a damp material that you're putting through. Otherwise, your non-conducting material will actually perform like a conducting material, because the layer of surface moisture on the surface renders it conductive, as it were. As with all physical separations, the closer the size particle size classification that you get and you produce from screening, etc., the better the separation efficiency you're going to get, because it allows us to optimize the separating conditions for a tight size range, which means the centrifugal force generated by the upper and lower band of the size range is going to be pretty much identical, which means that we can optimize the splitter plate position and the roll speed and achieve maximum recovery and grade of the material that you're wishing to separate. The final factor is limiting the amount of fines in the product. Minus 45 micron material tends to generate a lot of dust in the separating zone, which is not a good thing. It also tends to stick on the roll surface and be more difficult to discharge, so it's always good to dedust the material and remove those fines prior to electrostatic processing. And that's no different from most physical processing techniques like magnetic separation or air tabling as well. Machine variables are possibly more complex than a typical magnetic separation, because you have more things to alter on it. First of all, the applied voltage. For most recycling and mineral applications, we typically run at a applied voltage of 20 to 30 keV. If I'm doing a test on a material that I've not run before, I normally stick it at 25 keV and see how it performs, and then adjust accordingly afterwards. So separation control can be achieved by changing the applied voltage. If I start at 20 and don't get enough of the insulating material removed, I will raise the voltage to 30 keV. More material would stick, more of the middling fraction will stick as well, which will give me a cleaner conductor's material. So we can alter that variable. That's probably the first thing to think about changing. Roll speed can be used to project more of your conductors further. So if you're losing too much conducting material into your insulators, then a way of, because they may be non-liberated particles or something, then a way of getting over that is to increase the roll speed and get more of that material, get the centrifugal force greater than the image force, and separate that way. Higher roll speed also allows you to process a greater volume per meter per hour from the material. Splitter plate position, again, we look at the split like a magnetic separation application. We look at the splitter plate position and can cut accordingly depending on the discharge arc of the conductors and how high the pinning force is on our insulators, and move those accordingly. Low humidity atmospheric conditions, it's always good to have a relatively low humidity in the separating void of the electrostatic separator. So for applications that are in countries with high temperature and high relative humidity, then machine can be manufactured with heaters inside the separation cavity that will help control that and bring the relative humidity down. Electrode position is the final separating variable that can be moved to influence the discharge pattern of the conductors and the insulating materials. That tends to be used as a last of these options in the separation process. Normally, as I said before, we operate at about 45-degree angle from the perpendicular as a starting point. So applications, mineral processing, where they are used in conjunction with high intensity magnetic separators in separating complex materials like beach sand deposits, which may contain paramagnetic minerals such as ilmenite, chromonite, monazite and garnet, but they will also contain non-magnetic minerals such as zircon, silica sand and rutile. And those three that I've just mentioned have different conductivities, and the rutile tends to be quite conductive, the silica sand non-conductive. So you can obtain a separation between those two products. And the rutile is a high value material that goes for titanium dioxide manufacture. So it's worth recovering. It has a high value per ton. So it gives us the option of putting it through a separating flow sheet and obtaining better separation of some of the non-magnetic phases from a beach sand operation. Shredded waste electrical product or auto shredder residue, material also that is below 2 millimeters in size can be processed over these sorts of machines to obtain a conductor, non-conductor separation. Food separations as well. These machines were often known as tea separators because they were used to separate out the stalk of a tea leaf from the actual leaf itself, because one is a conductor and one is not a non-conductor. And it's a way of automating that sorting process. So if we talk a bit about mineral applications, all minerals have a signature conductivity, providing their relative humidity and the surface humidity is low enough. And electrostatic separation is used to separate out conductive minerals from non-conductive minerals on a number of applications. And this is a list of conducting minerals and non-conducting minerals. You can see conductors from the roll tend to be diamond, for example. Electrostatic separators can be used in diamond sorting as a method of separating the conducting diamond from the non-conducting silica minerals and things. We have things like galena, lead sulfide, hematite, some of our iron oxides here, rutile and excuse me, wolframite. Our insulators, which are pinned on the roll, can be mostly, again, tend to be the industrial minerals such as quartz, zircon, as well as sphalerite, which is an anomaly there, monazite and magnesite and gypsum. So sometimes, if we don't have a difference in magnetic susceptibility between these materials, we can achieve a separation by electrostatic separation. It's another string to the bow of a physical processing operation. If you look at the conductors and insulators for scrap applications, these are pretty much more clear cut, where we have materials like aluminium and copper, zinc, silver and gold, and platinum group metals particularly are conductive in nature. Our insulators are materials like plastic, glass and stone, fibres from circuit boards, etc. Ceramic capacitors from car shredding car engines and things, and rubber are insulating materials. So separations are possible from those. It is also possible to separate conductors from conductors, as it were, if there's a significant difference in conductivity between one of these and one of these. For example, aluminium and copper, it is possible to separate out the two products simply by a difference in conductivity. One is more conductive than the other, and by setting the machine up correctly at a relatively low KeV, then we can separate one from the other, should you wish to. Typical recycling applications, capacities per meter width of electrostatic roll, would be copper plastic separation maybe for a granulated cable, 2 to 3 tons per hour. Aluminium copper separation, 3 to 4 tons per hour, because we don't have the plastic there, we've got a denser material. WEE separations, waste electrical product separations, 2 to 3 tons per hour. So reasonable capacities per meter wide unit. Mineral applications, rutile quartz separation, they're both relatively low density, in the region of 2.63 specific gravity. So at a lower capacity, 1 to 2 tons per hour, but the rutiles are valuable material, so we trade that off as a viable process, as it were. Some of the more denser materials like wolframite and quartz separation, 2 to 3 tons per hour per meter width of unit. So an example of a separation. This is a copper aluminium separation that we have run on a machine. This machine is in the laboratory at the University of Birmingham, but is similar in design to the one made by Buntings. And we'll have a look at the separation of this. This is a physical separator used for the separation of materials of different conductivity. This is what's called an electrostatic or high tension roll separator, and is used a lot in the mineral processing and metal recycling industry. So if you want to come in and zoom in on the roll, you'll see here we have an earthed roll with a titanium face upon it, and we also have the wire there is a high tension corona discharge system, which puts through about 20,000 kV through it. Our feed material for this particular demonstration is 50-50 mixture of copper and aluminium, and what I'm going to try to do is separate the material based upon their individual conductivities. The aluminium has slightly less conductivity than the copper. What will happen is when I pass it off the vibratory feeder onto the roll, the particles will be charged by the corona discharge system here. When they hit the earth roll, the material that has the highest conductivity will discharge its charge quicker to the roll and be thrown off by its own centrifugal force, and material that is less conductive will keep it what's called an image force on the roll surface and be attached to the roll and be discharged around the other side of that splitter plate there. This material is probably about 1 millimeter down to about 500 microns. Wouldn't be separated on an eddy current separator. Here you can see, in this case, we have the heater situated above the vibrator feeder. It's not always the case that you need that. So we've got a relatively slow speed and slow feed rate. The fractions that we have from this test are in the tray here. We have for the sake of the test, the non-conductors, which are here, which you can see are predominantly aluminium with a tiny bit of copper fines within that material. So it needs closer size classification to get a perfect separation on that. And we have our copper here, which was thrown from the roll because it has more conductivity. There we have some aluminium in there, but that's a larger size range. So again, if I screened it at a slightly different size range, I'd be able to get an effective separation between the copper and the aluminium. What these would then go to is a second separator, which would recover the electrostatic separator that will recover some more of the aluminium to give you a final product that would be 98 to 99% pure metal. So a simple way of producing material that is too small for an eddy current separator, but these, instead of being a mixed conductor fraction, which this was 50-50 to begin with. After one pass, I've got a pretty good aluminium concentrate. I've got a copper concentrate here that can be further processed for upgrading using a simple roll separator in a dry process, which will take, you know, a metre wide unit will take 3 to 4 tonnes per hour of material for processing. So again, just to confirm that we can use our electrostatic separator to separate out material that is conductive and non-conductive. That's a relatively easy separation, but we can also use it to separate a conducting metal from a conducting metal based upon their relative conductivities. So something that you may consider two highly conductive metals can be separated because they have a difference in conductivity, as it were. So that concludes our presentation. I hope you found it of interest. If you have or wish to have any test work carried out on the electrostatic separator or magnetic separators, then please contact us through our website. Thank you for your attention.